Hello, BC Calc. This is your day 111 notes. Today we are looking at the calculus of power series. So if you have day 110 nearby, we're certainly going to be referencing some of the same type of terminology and vocabulary from day 110, including this first example, finding the interval of convergence. So go ahead and take a look at this series, write out a few terms for me, and then see if you can use a test to determine what the interval of convergence would be here. Don't forget that once you get your interval, you have to check the endpoints to see if it converges at either of those. So please make sure you consider that. But this is something we will go over next time we are in class together. So take a look at that one. We'll go over it next time. All right, let's actually move on to the next page where we're going to get into differentiating and integrating power series. So if we have a power series of this form, C sub n times x minus a to the n, if we know that it converges, then what would f prime of x and what would the second derivative f double prime of x look like? Well, it would start looking like the following. F prime of x would be, using our power rule, n times c sub n, and then x minus a to the n minus 1 power. Okay, so for a power series that converges, we know we would have a second derivative equal to the following, right? Just use the power rule again, bring down the n minus 1. Times c sub n, x minus a is now to the n minus 2 power, and so on. And we can find however many derivatives we'd like. Now, keeping in mind within the series, which is the sum of all those terms, we can find the derivative of each because we know the derivative of a sum is equal to the sum of the derivatives. So we can find the derivative of each term, including what we're going to be concerned with today is thinking about what is the derivative of the nth term. And how can the derivative of the nth term give us some information about what function f of x we're looking at? So that's what we're going to be looking at today. If we have a series that converges, how can we use the information about that series and maybe its derivative to be able to come up with what the function f of x is? You're going to see some very surprising results today. All right, same thing would happen for integration. If you have a function f of x that converges, its integral would converge as well. So we would just use, in this case, the anti-power rule, where you'd have c sub n x minus a up this by 1 to the n plus 1 now, and then divide by n plus 1, and that would converge as well. So what are we going to be really building towards today? I've already described it a little bit. Today, what we're going to see is we're going to use this to get a function f of x that approximates the infinite series, which is what it would converge to. Okay, so we're going to take the terms within the infinite series, find a derivative, see how that can help us get some information about the function f of x. And then where we're headed even beyond that, later on, as we finish up chapter 9, given a function, we can find a series to approximate it. So these are all some major connections that we can make within our unit of series to be able to take an infinite series and represent it as some function f of x. And we're going to get into practice with that right now. So let's take a look at this example on the next page. We have f of x equals the sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the 2n minus 1 over 2n minus 1. So if we start plugging in values for n here, when n equals 1, this would be negative 1 to the 0, so that's going to be a positive term first. We're going to get x to the first over 2 times 1 minus 1 would be 1, so the first term is x. And then the signs will alternate, right? So we're going to get minus for the next term. If we plug in n equals 2, there's going to be x cubed over 3. And then plus, the next term would be x to the 5th over 5, and then so on and so forth. We would get the resulting terms from there. So just to get an idea of what's going on here, if I said, hey, let's find f prime of x, let's find the derivative here. Well, the derivative would be for each of these terms individually using the power rule, it would be 1 for the first term minus, let's say 3 times the third would just make that 1x squared. Then it would become plus x to the 4th, and minus so on and so forth, x to the 6th, and we can see kind of the pattern that's emerging here. So therefore, the derivative of the nth term would be the following. If this is the expression that represents the nth term, f prime of x would be negative 1 to the n minus 1. So that's going to be constant there. And then use the power rule there. So it's going to be 2n minus 1 comes down times x to the, subtract 1 from that exponent. So now it's the 2n minus 2 power. Okay, and remember, 2n minus 1 in the denominator is also a constant in terms of n. So these constants then drop out. And it turns out that the derivative of the nth term is representative of the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x to the 2n minus 2. And what that series results in is the series that we started to develop right here. So here's what it looks like in terms of the nth term. Okay, but if you plug in 1 here, you're going to get negative 1 to the 0. Plug in 1 there, you get x to the 0, which is 1. If you plug in 2, this becomes negative 1. Plug in 2 here. The next term becomes, that's going to be x squared up in the exponent. And you're going to generate that same exact list that we had for f prime of x here a moment ago. So it's good to have both skills, to be able to analyze within an expanded out number of terms what the derivative is, but then also just to find the derivative of the nth term, plug in values like 1, 2, 3, and confirm that it matches that same series there. So what are we looking at here? We're looking at a series that it turns out that it's geometric in nature. Right? So if we think about what the ratio is that I'm multiplying each time by negative x squared. And if this is a series that converges to some function f of x, then we know that it has to follow the form of an infinite geometric series. So for an infinite geometric series, we would have a1 over 1 minus r, which in this case would be a1 of 1 over 1 minus the ratio negative x squared, which is 1 over 1 plus x squared. So it turns out we can write this infinite series because it converges and it's geometric as the function 1 over 1 plus x squared. So that's what f prime of x equals. F prime of x is equal to 1 over 1 plus x squared. Wait a minute, though. We recognize that if the derivative is 1 over 1 plus x squared, we know what f of x is, don't we? Well, we better know what f of x is, right? That's what we're trying to find. What does f of x equal? If the sum of these terms, what is that approximating if that series converges? It's approximating tan inverse of x plus c. Right? If you find the antiderivative, 1 over 1 plus x squared, that's tan inverse. Crazy. Okay. Let's talk about an initial condition here. So the initial condition would be that if we plug in 0 for x, that's the easiest initial condition to pick, that we would get 0 for y. So if we plug in that initial condition, tan inverse of 0 is 0. So we're just going to get that c equals 0 because of this initial condition. So therefore, we get f of x equals just tan inverse of x. And the really cool part of this is, of course, we can check on the calculator to see, does the function tan inverse have an approximate infinite series equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. And of course, the more terms you put in there, the more accurate that series will become. So I've actually already typed this in. We've got tan inverse in y1. I made a bold graph of, I went out to the term with x to the 7th over 7. So I'm going to zoom 6 here, see what happens. Here's my graph for tan inverse. And then the polynomial with 4 terms written in it looks like that. So I don't know if that was a surprising result or not to you, but I mean, it's not a perfect fit everywhere because we clearly can't write out the infinite number of terms, but it's a pretty good fit right around the origin there, isn't it? Right around x equals 0. In fact, if I zoom in for you right here, right at the origin, you're going to see a fantastic fit for tan inverse and the infinite series that we just determined. Okay. So I think that's pretty neat, that if I had gone out even to the next term, the x to the 9th over 9 and x to the 11th over 11th, you're going to start seeing this function extend out even further to even be a better fit surrounding the origin there. So that's kind of the main idea of what we're headed towards, is taking an infinite series that converges to some function f of x and determining what is this function f of x. Okay. And the best way to do that is by finding the derivative of this power series, such that if I know the pattern within the derivative, because it's a geometric series, we can then integrate and figure out what's the original function. Tan inverse is what we're looking at there. Crazy stuff. Let's try another one. All right, so the last one that we'll do in today's notes is the sum from n equals 1 to infinity of -1 to the n minus 1 over, or times x to the n over n. When x is 1, this is just +1, so x to the first over 1 is x. And then the next term is going to be minus because of the alternating piece here, so x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. So that's what the series is going to look like when expanded. All right, let's just go right to the derivative of the nth term here. So f prime of x in general, using the nth term, it's going to be -1 to the n minus 1, and then n times x to the n minus 1 over n. Remember, n is constant, right? So we're going to leave that n on the bottom such that those n's now cancel out. So we get that the derivative is the sum from n equals 1 to infinity of -1 to the n minus 1 times x to the n minus 1. All right, what do we want to do? We want to see what do the terms look like in this series so that I can get an idea as to what type of series we're looking at and then determine when it might converge. So if I plug in 1, this is going to be a first term here of x to the 0, which is 1. And then the signs will alternate from there. So minus, when n equals 2, you get x to the first. If n equals 3, you get plus x squared minus x cubed, and so on from there. Okay, so that's what the series is going to start building out towards. Well, that's an infinite geometric series again, except this time my ratio is -x. Okay, so if we're multiplying by -x each time, the infinite series would be a1, which is 1, over 1 minus the ratio, -x. So we get that the infinite series is equal to 1 over 1 plus x. And again, that's f prime. So f prime is equal to 1 over 1 plus x. And therefore, f of x would be the antiderivative of 1 over 1 plus x dx, which not tan inverse this time, but something we could find just as easily. This is just natural log. So it's going to be that f of x is equal to the natural log of 1 plus x plus c. And just like we did before, we want to consider an initial condition. So what is the initial condition we should pick? Well, when x equals 0, what do we know to be true? If x equals 0, if those are all zeros, y is 0 as well. So if I plug in that initial condition, we get 0 equals the ln of 1 plus c. Ln of 1 is 0. So we actually do get that c equals 0 again. And therefore, the function that approximates that infinite series is ln absolute value of 1 plus x. Okay, if you want to check it on the calculator, go for it. Maybe we'll do that next time we're in class together. But I just think this is so fantastically awesome. How we can find the derivative of a power series, see the patterns for that geometric, write f prime, and then work backwards to find f of x. So cool. All right, so we'll do a little bit more calculator practice next time and talk a little bit more about power series here. But that's it for today. Have a great rest of your day.